Good morning everyone. In this session, we will discuss about the computation of slope and deflection of the beam using conjugate beam method. This method is often used to derive the slope and deflection of a beam when subjected to an external load whose flexural rigidity is not uniform throughout its length. This method is very useful in finding the deflection even if there is no point in the beam where the slope is zero. Conjugate beam is defined as an imaginary beam with the same length as that of the original beam, but the load at any point on the conjugate beam is equal to the bending moment at that point divided by EI. This method was developed by H. Muller Barcelo in 1865. The figures shown here depicts both conjugate beam and the real beam. M by EI diagram in conjugate beam is equal to loading in case of real beam. If M by EI diagram is positive in conjugate beam, that means loading will be acting downwards in the real beam. The conjugate beam method is an extremely versatile method for computation of deflections in beams. The relationship between the loading, shear and bending moments are given in equation 1. That is, d square m by dx square is equal to dv by dx. This will be equal to minus wx, where m is the bending moment, v is the shear force, and w of x is the intensity of the distributed load. Table 1 displays the transformation of the real beam to conjugate beam. In this process, the hinged support and roller support remains same in case of real beam and conjugate beam, as shown in this table. The fixed support in the real beam will be transformed to a free end in case of conjugate beam. Similarly, free end in the real beam will be transformed into a fixed end in case of conjugate beam. If there is an intermediate support in real beam will become an internal hinge in case of conjugate beam. Similarly, internal hinge in the real beam will be transformed into an internal support in case of conjugate beam. Table 2 displays the transformed conjugate beam with respect to real beam. Both slope and deflection in any beam at any point can be determined using conjugate beam method using the following theorems. Theorem 1. The slope at a point in the real beam is numerically equal to the shear at the corresponding point in the conjugate beam. Theorem 2. The displacement of a point in a real beam is numerically equal to the moment at that corresponding point in the conjugate beam. There are two major steps in the conjugate beam method. The first step is to set up a conjugate beam, and the second step is to determine the shearing forces and the bending moments in this beam. Here, figure shows the real beam as well as the conjugate beam. The real beam is loaded with uniformly distributed load of W kilonewton per meter, and the conjugate beam is loaded with bending moment diagram. First, let us consider a part of the real beam, an element of length dx. It is as shown here. Similarly, we will consider an element strip of length dx in the conjugate beam. The load in the real beam, W kilonewton per meter, will be equal to the M by EI diagram of the conjugate beam. This will be equal to W into dx. According to bending theory, M by EI is equal to d square y by dx square. This will be equal to W, that is loading. In order to get shear force, equation 1 need to be integrated. Shearing force V is equal to integration of W into dx. Here W is equal to M by EI. So substituting the value of m by ei, we will get integration of m by ei into dx. This will be equal to d square y by dx square into dx in the integration form. Therefore, shear force V will be equal to dy by dx. This will be equal to slope theta. In order to get bending moment, equation 2 need to be integrated. Bending moment m is equal to integration of v into dx. Here v is equal to dy by dx as we already derived it. So integrating this dy by dx, we will get y. This y is called as deflection, that is delta. Therefore, y is equal to deflection. This will be equal to bending moment. Y dash will be equal to dy by dx. This will be equal to slope or shear force. Y double dash will be equal to d square y by dx square. This will be equal to loading. Positive shear force in the conjugate beam equals to the positive slope in the real beam. And positive moment in the conjugate beam equals to a positive deflection of the real beam. This is as shown in the figure. Procedure for analysis by conjugate beam method. First, we need to draw the curvature diagram for the real beam. Second, draw the conjugate beam for the real beam. The conjugate beam has the same length as that of the real beam. A rotation at any point in the real beam corresponds to a shear force at the same point in the conjugate beam, and a displacement at any point in the real beam corresponds to a moment in the conjugate beam. Next, apply the curvature diagram of the real beam as a distributed load on the conjugate beam. Using the equations of static equilibrium, determine the reactions at the supports of the conjugate beam. Determine the shear force and moment at the sections of interest in the conjugate beam. These shear forces and moments are equal to the slope and deflection, respectively, in the real beam. Positive shear in the conjugate beam implies a counterclockwise slope in the real beam, while a positive moment denotes an upward deflection in the real beam.